Hello and welcome. Generative adversarial networks were, like variational autoencoders, invented roughly 10 years ago. This groundbreaking paper presented a new approach to generative modeling based on a two-player game. It introduced a fundamentally different perspective that has proven remarkably effective and has become one of the cornerstones of modern generative modeling. The original paper is again a bit technical, focusing on the mathematical formulation of the adversarial training process. It describes the GAN process in terms of game theory, specifically as a minimax two-player game. We will return to this theoretical basis once we have an intuitive understanding of what these GANs do. So, what are we supposed to learn about these GANs? We start by introducing the basic architecture of a generative adversarial network, shortly GAN. We build and train so-called convolutional GAN, or DC for deep convolutional, and use that for generating images. GAN training suffers greatly from instability. The loss values tend to oscillate back and forth. Other problems include so-called mode collapse, to be explained, and of course vanishing gradients. So-called Wasserstein GAN, WGAN architecture addresses these problems, especially the instability. We will build and use such a WGAN with a gradient penalty. Conditional GANs, C GANs, sometimes the C is with the lowercase c, they allow us to control what kind of data is generated. By providing additional information as a condition, like a class label or attributes from the celebrity dataset, we can generate specific outputs, such as faces with mustaches. We will see how to build, train and use a conditional GAN. While considering these goals, I will mix in the relevant and, in my opinion, necessary theoretical background. This is needed especially to explain the transition from the initial GAN idea as a two-player game to a better informed version or versions like the Wasserstein GAN. The textbook starts again with a short story to illustrate some of the fundamental concepts used in the GAN training process. Here's a revised version of that story. You are the head of quality control at the Lego brick factory. There's a notorious competitor out there making out counterfeit copies of your nice bricks, trying to undermine your brand and business. This crafty rival has managed to sneak their fakes into your packing line, mingling them with your genuine products before they are dispatched to customers. Your mission is to detect and eliminate these impostors before they reach the market. As you become adept at spotting the fakes, the competitor reacts, refining their counterfeits. to make them harder to distinguish from your authentic bricks. You then retrain yourself, sharpening your skills to identify these more sophisticated fakes. This back and forth continues, with each side pushing the other to improve. Theoretically, this could go on until neither can enhance their strategy further, reaching what is known in game theory as the Nash equilibrium. GAN concept in a nutshell. The forger is now called generator because it generates fake data. The quality control is called discriminator because it discriminates between real and fake data. We have a game of 2 players where the generator aims to create realistic synthetic data like images, typically from random noise. And the discriminator tries to distinguish between real data and the generated fake data. Initially, neither one is very good in their jobs. Generator produces poor quality outputs and discriminator makes random guesses. Then starts a process we call as adversarial training. The generator and discriminator are trained alternately. As the generator improves, the discriminator must also improve to maintain its accuracy and vice versa. This ongoing arms race drives both networks to become more sophisticated. The ultimate goal of GAN training is not for either player to definitely win. While the discriminator would win if it could detect all fakes with 100% accuracy, and the generator would win if the discriminator couldn't distinguish between real and fake. It would have 50% accuracy, essentially guessing or tossing a coin. These are not the primary objectives. To conclude, the true goal of GAN training is to train a generator capable of producing high-quality realistic data from random noise. In order to achieve this goal, the generator needs a strong, not weak, discriminator as its opponent, and an opponent that can provide meaningful feedback to guide the generator's improvement. This textbook figure illustrates this arrangement. Generator outputs fake images from random noise. Discriminator then predicts whether a given image is fake or real. Real images should be given high probabilities of being real and fakes low probabilities of being real. That's all for this time. On the next lecture we'll build our first GAN.